participants? I think there is no question. So thanks again, Dr. Usmanigar. Our next presenter is ID number 47, Dr. Ataullah. Welcome, ma'am. And Dr. Ataullah, are you available, sir? And Dr. Ataullah, are you available, sir? I think he is not available. So let's move to next participant, Mr. Sunusi Haruna, Senior Lecturer, Department of Arts and Humanities, Kano State Polytechnic, School of General Studies, Nigeria. Mr. Sunusi Haruna, are you available, sir? Am I audible to all of you? I think some technical issues there. Mr. Mohammad Fayaz. Mr. Mohammad Fayaz.
Yes, sir.
Okay, sir. Kindly share your screen.
Okay.
Now, our presenter is ID number 49, Mr. Mohammad Fayaz. He is a research scholar in the Department of Applied Mathematics, Institute of Numerical Sciences, Kohat University of Science and Technology, Kohat from Pakistan. His paper title is Numerical Solution of Time Fractional Reaction Diffusion Coupled Equations in Biological and Chemical Systems. I request Mr. Mohammad Fayaz, kindly share your work.
Sir, can you see my screen?
It's visible, sir.
Hello. Yes, sir. Can you see my screen? I observed it. Can you see it?
Yeah, your screen is visible.
Okay, sir.
You can proceed.
I'm thankful to this. First of all, I'm thankful to this the whole team that who can invite me for this conference. And I'm from Pakistan. My name is Mohammad Fayaz, and today my topic is numerical solution of time fractional reaction diffusion coupled equations in biological and chemical systems. So the layout of my work is that first of all I will discuss about the motivations, and second one is fractional integration and yes, sir.
Your screen is visible but not clear. Kindly maximize it.
Okay, sir. Okay.
It's visible but not clear.
Okay, sir. I'll. And now, is it clear?
Yeah, now it's okay. Kindly proceed.
Hello, sir. Now is it clear?
It's clear, sir. Please proceed.
Hello.
It's clear.
Can you hear me, sir? Hello.
Mr. Fayaz, it's visible now. It's clear now. You can proceed.
Hello.
Yes, sir.
Am I audible to you?
Yes,
Hello?
yes, you are audible.
You are audible, sir.
And also your screen.
Mr. Fayaz,
Hello.
Mr.
Am I
Fayaz,
audible to you?
yeah, you are audible. Kindly share your screen. Use your mobile screen as landscape.
Hello.
Am I audible?
Yes, sir, you are audible and your screen is also very visible and clear. Kindly proceed.
Okay, okay, sir. So my topic layout is, first of all, I will discuss about motivation, and then I will discuss fractional integration and as derivative, and then proposed methodology, test problem, and conclusion. So motivation, fractional or non-integer calculus is concerned with derivative and integrals of the arbitrary orders. Just like we learned about the derivative about the first order, second order, third order. So now we will discuss only about the fractional order, means 1 over 2 time, 1 over 3 time, 1 over 4 time. So it was provided a scientific discussion between the Hospital and Leibniz in 1695 and was remarkably described by the eminent mathematicians such as Euler, Abel, and Riemann, which is discussed in the reference number 1. Fractional calculus has given more emphasis from the last few decades because it has the many applications in science and engineering. Just like you can see that in electrochemistry, the electric current is linearly related to the temporal derivative of the concern, which is given in the following equation number 1. In the same way, in the viscoelasticity fractional order model approximation and the viscoelastic materials behavior of material through the corresponding fractional differential equation, which is given in equation number 2. So now our target is that how we solve these differential equations which involve the fractional order derivative. So for this, most analytical solutions of the partial differential equation involving the fractional derivative is not easy to compute. So therefore, we use the numerical method are required. So now what is fractional integral and fractional derivatives? So this is the definition of fractional integrals. So let negative infinity a less than xi less or equal to b less than infinity, then for the locally integrable function f of x, the Riemann-Leibniz fractional integrals of order alpha greater than 0 as defined, which is given in this equations. You can see that the first one is called left sense and the second one is called the right sense. So now we will discuss about the Riemann-Leibniz derivative and Capacitance derivative. So the function f of xi in the interval a to xi, the alpha greater than 0 order of fractional derivatives and RL form of 3 is written as, just like you can see in the equation number, that the first equations, this definition is called Riemann-Leibniz form of the fractional order derivative, and the second one is called the Capacitance fractional order derivative. So now we will discuss about the proposed methodology. So just like you can see at the start of my topic, the topic name is reaction diffusion equations. So these are the generalized form of the reaction diffusion equations. So many mathematicians can solve these type of differential equations for the integer order and the temporal derivative. So now my work is that I can convert the temporal derivative to the fractional derivative. Then they will get a source function which can be added to the right hand side. Then they will become the exact differential equations. You can see in equation number 3, I can take the temporal derivative at the left hand side and I will add the source function to the right hand side. So they will become the coupled equations you can see in equation number 3, where aj, bj, and cj up to kj are the real constant, where G is equal to 1, 2, where F1 and F2 are the source function and the special domain is considered to the x0 to xn. So now, my work is that you can see that they have too many initial condition and boundary conditions. So first I will discuss about the initial condition. You can see that ux comma 0 is equal to u naught and vx comma 0 is equal to v naught. In the same way, we can use the boundary conditions, which are too many types. So you can already learn about it. There are three many types of the boundary conditions. First one is called the direct condition. You can see that they have no derivative. And the second one is called mixed derivative condition. They have, one is the free of derivative and second one contain derivative. And the third one contain both have the derivative are called Newman boundary condition. So we will use these three type of boundary condition in our research work. So now you can see in the equation number 3, the left hand side contain the temporal derivative of the fractional derivative. So now we will discuss about the temporal derivative. You can see that this is the definition for the temporal derivative of u and temporal derivative of v in the fractional order, which can be seen in that equation number 8 and equation number 9. So now we have a technique that we have approximate these derivative by the quadrature rule. This is the quadrature rule. You can see that in equation number 10 and 11, these are the quadrature rule. The Kapotto fractional derivative can be approximated by the simple quadrature formula as follow equation number 10 and equation number 11, which is discussed in the reference number 5. So now we will use the Euler implicit scheme to the equation number 3, which is discussed in the start of the slide for methodology. So we will use the implicit Euler scheme. Implicit Euler scheme is that you can take the left hand side term at the n plus 1 time level. You can see that I take all the term at the n plus 1 time level. So now, what is un? Un represent ux comma t to the power n, and the same way f1 is represent f1 comma x comma t to the power n, in the same way you can see that. So now we will use the equation number 10 because you can see that the equation number 12 and 13, the left hand side contain the temporal derivative. So now we will put from the equation number 10 and 11 here equation number 12 and 13 by the quadrature rule, which can be seen in the equation number 10 and 11. So now we will use the quadrature rule in equation number 12 and 13. We will get the equation number 14 and 15. So after one term expansion and the resultant as we can see that equation number 16 and 17. And at last, rearrange the terms, equation number 16 and 17 means all the term which contain n plus 1 time derivative on the left hand side and all the term which contain the nth at the nth term contain on the left hand side. So we will get equation number 18 and 19. You can see that. So there are too many nonlinear terms, u square v, uv, and u dot v square. So now we will linearize by this. You can see that the nonlinear term u square v and so on are linearized by the following formula, which is discussed in the reference number 5. So now we will linearize this term by this method. This is called quasi-linearization method. So equation number 20, 21, 22 are the linearization methods which is discussed. So now we will what? So inserting the central difference formula for the uxx to the power at the n plus 1 time and v double x at the n plus 1 time, and equation number 20, 21 and 22 as used and equation number 18 and 19. So we will get the this type of matrix a dot w to the power n plus 1 is equal to w to the power n. So we have learned about the three type of boundary conditions. So we will get three type of matrices. So for type number 1, which is discussed about the direct condition, we will get A is equal to 2m minus 2 multiplied by 2m minus 2 cross matrix, and Wn will be equal to 2m minus 2 multiplied by 1 matrix. And for type 2, you can see that, and for type 3, we will get this type of matrices. So now we will, from the above scheme, we can approximate the solutions at different time level, because we learned about that we will find the solution of these type of the differential equations which have the temporal derivative. So this is the required scheme. So this is the required methodology which is making for the solution of the differential equations. So I have already learned, I said that about that. Then we have the two many types of the reaction diffusion equations. So I will discuss there only two equations. First one is called linear and the second one is called Saknakenborg model. You can see in the table, these are the required parameters which can be replaced by these parameters. So now we will discuss about the test problem. Here we apply the proposed methodology for some linear and non-linear model. Linear means which is discussed in the first row of the table 1 and non-linear which is discussed in the second row of the table. So I will check and in order to check the efficiency of the technique, we can compute the absolute error L2 and L infinity norms, which is obtained by the reference number 7. You can see absolute error L infinity and L2 norms, which can be found by this way. So first of all, I will discuss about the linear problem. In this section, we discuss about the linear model, which is discussed in the first row of the table number 1. This is the required linear model. And they have the initial condition and boundary condition you can see in equation number 14 and 24 and 25. So the closed form solution, closed form means the exact solution of these differential equation as that u and v, which you can see in the slide number 21. So these are the exact solution of the linear problems. So now what we will do the approximate solution for this, because we are learned about the numerical solutions. So they have 3 types of the questions. In linear problem, we have discussed 3 types of the question. First one is called diffusion dominant case. Diffusion dominant case means because A is equal to 0.1 and B is equal to 0.01 and D is equal to 1, where D represent the diffusion constant. You can see in the equation number 23, the D represent because D multiplied with the diffusion element, so D represent the diffusion constant. So that's why this case is called diffusion dominant case because D is greater than. And the second one is called reaction dominant case because it have A is equal to 2, where A is the reaction, A multiplied by U, where U is the reaction and A is the constant of the reaction. So that's why this is called the reaction dominant case. And third one is called reaction dominant with step reaction because it have A is equal to 100 and B is equal to 1. So now we will discuss about these 3 methods. So the first, you can see about the diffusion dominant case, the first case. When I solve this question by the proposed methodology, proposed schema, so I will get this type of norms. You can see that the table number 2 represent the L infinity norm, which can be, you can see that the first column represent the alpha is equal to 0.25. Alpha means the derivative. We need 1/4 time derivative. So I can solve this question for this type of derivative. I will get these results. And the same way 0.5 and the same way 0.75 and the same way for alpha is equal to 1. And the table number 3 represents for the diffusion dominant case, but the L2 norm, you can see that here. So in the same way, these are the required result. The first row shows that the first figure is the exact solution, and second one is approximate, and third one is the error between these 2 terms. And the second row represents the solution of V. The first element represents the V, the exact of V, and the second element represents the numerical solution of V, and the third one is the error between these 2 terms. So this is the table number 4 and 5. L infinity norm for the distinct value of alpha at the different time level, and the reaction dominant means case number 2. So now we will discuss about the reaction dominant case. The first one, the table number 4 represents the L infinity norm, and table number 5 represent the L2 norm. In the same case, these are the first row represent the solution of U, and the second row represent the solution of V. And the last one, this is the L infinity norm of the distinct value for at the 3. So we will the table number 6 represent the L infinity norm, and table number 7 represent the L2 norms. So this is the required figure. The first row represents the solution of the U, and the second row represents the solution of V at t is equal to 0.001. So this is all about the result of the linear problem. So now we will go to the nonlinear problem means Saknakenborg model. This is the required Saknakenborg model, which is discussed in the second row on the table number 2. So they have the same initial conditions. You can see that where A is equal to too many parameter, A is equal to 0.12 and B is equal to 0.79, D is equal to 10, gamma is equal to 100, and 5,000 is at the parameters. So these are the initial conditions and boundary conditions. So we will solve by the proposed technique. We will get the required result for the relative error for the Saknakenborg model. You can see there. This is the required relative error. because this model have no exact solution, so you will only find the relative error for this at different time level at different alpha. For alpha is equal to 0.25, alpha is equal to 0.5, and alpha is equal to 0.75, and alpha is equal to 1. So these are the required result. The first row shows the required result for gamma is equal to 10,000, and the second row represents the solution for the gamma is equal to 500. So at last, at the conclusion of this work is that in this work, the finite difference method is implemented for the sum time fractional reaction diffusion equations. The performance of the proposed method is checked by the norms L2 and L infinity you can see in the too many tables. The computational solution is compared with the exact solution form you can see in the linear problems. It is observed that the scheme works for the time fractional reaction diffusions coupled equations. So thank you.
Thank you so much, sir. You have presented very nicely. Thank you so much. Is there any question from the participants?
Thank you.
Any question from the participants?
Yes, I do have. Okay, shall I continue? I do have questions.
Yeah. Please, sir.
Muhammad.
Yes, sir. Yes, sir.
Thank you for your nice presentation.
Thank you, sir.
I do have some couple of questions. So, to discretize your problem, you used that of Euler's method.
Yes, sir.
Yeah, we know that Euler's method is a lower order method. Why don't you use the other higher order methods? Just the like of that of Ramta method. I'm sorry, Crank-Nicholson method.
Sir, the Euler method is the basic method, but now we will talk about the fractional derivative. So that's why I will use this method for the fractional order derivative.
Okay, that's good. The other question is that I think for the nonlinear case,
yes, sir.
The problems do not have exact solution.
Yes, sir.
So how did you just got the error? If there is no exact solution, how do you?
Sir, so here I will find the relative error. Relative error means so you will find the error between the last two times, last two intervals.
I know that, for instance, relative if the exact solution is there, the relative error is the absolute value of exact solution minus that of numerical over exact solution times 100.
Yes, sir.
So how did you get the relative error there if there is no exact solution? What method you have used?
The solution.
I want you to know the method you have used. It is possible to find if there is no exact solution.
Yes, sir. Sir, this method have no exact solution, so that's why we will find the relative error. Relative error means which I show the formula in the slide number 17. So that's why I will use the relative error because we will find the difference between at the last two terms, n into n plus 1 time level.
Okay, that is possible. Why don't you use double mesh principle? Double meshing principle is also possible. I expected that you have used the double meshing principle if there is no exact solution.
Yes, sir.
Okay, leave it anyhow. Thank you very much.
Okay, sir. Thank you.
The other question, sorry, before my final, you have used the L2 norm and that of L infinity norm. Which one gives better approximation? Between L2 and the L infinity norm, which one gives better approximation for your problem?
Yes, sir.
Look, to show us the error you obtained for your problem, you used L2 and the L infinity norm.
Yes, sir.
Both L2 and the L infinity norms are used to show the magnitude of the error. Is it L2 or L infinity norm which gives the better approximation is my question, please.
Sir, L infinity have the best approximations.
Yeah, L2, that's nice. Thank you.
Yes, sir. Thank you, sir.
Okay, thank you so much, Mr. Mohammed Fayaz.
Thank you, sir.
Now I request Mr. Sunusi Haruna. Senior Lecturer, Department of Arts and Humanities, Kano State Polytechnic, School of General Studies, Nigeria. His paper presentation title is An Evaluations of Equilibrium Points of the Photogravitational Restricted Three-Body Problem with Oblateness under a Heterogeneous Spheroid. Sir, are you available?
Hello.
Yes, sir. Kindly share your screen.
Good afternoon, ladies and gentlemen. My name is I'm here to present my title, Things of the Equilibrium Points in the Restricted Three-Body Problem. Yes, sir.
Yes, sir. Share your
Let
screen,
me try
sir.
to show the
Okay.
content. So let me share. Yes, sir. I'm trying to share.
Okay, sir.
I'm trying to share. Problems with the connections, network problem crashes. Please give another chance so that when I get ready, so that I will present later.
Okay, thank you, sir.
So can you hear me, sir?
Okay.
Yes, thank you very much.
Now I request Mr. Tasfai Magreza. He is a lecturer in the Department of Mathematics, Walkite University, Ethiopia. His paper title is Uniqueness of Common Fixed Points of F contraction mapping with generalized altering distance function in partially ordered matrix spaces satisfying occasionally weakly compatible mapping. Mr. Tasfai Magreza, please share your screen, sir. Mr. Sunusi Haruna, kindly stop sharing your screen, sir.
Yes, sir. Yes. Okay, sir. Thank you. Thank you. I have problem with the network.
I think there is some connection problem from Mr. Tasfai's side. Mr. Neeraj Kumar, are you available, sir? Sir, yes. Mr. Neeraj Kumar, ID number 51. Okay, I think he is also not available. Mr. Alamzod, ID number 52. Mr. Alamzod. Mr. Alamzod.
I'm available here.
Okay. Now I request you to kindly share your screen.
Okay. Okay, what's this one?
Children doesn't share lens and then ina gama shi a albarin samu gama da yanzu tun da sun fita ma ni share in kuma ya share
What he is sharing?
da shi ne
Mr. Alamzod, kindly share your work, your PPT presentation.
da shi ne ke share ya kasa share
He's presenting hours.
ma an faɗi suna na gaba sun ce da yanki kan
Mr. Alamzod, are you able to to share your screen, sir? Okay, now I request to Mr. Gizo Debito. He is the lecturer in Department of Mathematics, Mizan-Tepi University, Ethiopia. His paper title is Numerical Solution of One-Dimensional Schrodinger Equation Using Radial Basis Quadrature Method and the Cubic Spline Functions. Mr. Gizo? Mr. Gizo? Am I audible to you? Mr. Gizo, am I audible to you?
Yes, yes.
Okay.
Is it visible?
It's processing.
Okay.
Just wait. He has to come here.
It is visible?
It's not visible.
Who is doctor? Stop. Share. Share. Yes. Share. Is it visible, doctor?
It's still not.
Doctor, please unshare your screen.
Your screen is not visible, sir.
Please unshare your screen.
What?
Please unshare your screen, doctor.
I'm not sharing the screen.
Please put there to stop. Salam.
Mr. Alamzod?
Screen, okay. Screen, share my screen.
There you call this up. Yeah. Yeah, yeah, your system. Wait, you call here. Come here. You can here. Yeah.
Mr. Alamzod, am I audible to you?
You like huh? Like yes.
Mr. Sunusi Haruna.
No, you can sir. Gizo.
Gizo.
Okay.
Mr. Gizo, your screen is visible. You can present now.
Make it full screen. Enough, sir.
Mele. Sí, que nacido para acá. ¿Venía para acá, no? Ariana? Da Javier para acá, va para acá.
Please.
Okay. Can I start? Is it visible? Can I start?
First share your screen. Your screen is not visible.
Wait, doctor. Okay. Is it visible?
Yes, it's visible. You can present now.
Okay.
Make it full screen.
Make it full screen.
Okay, thank you first for the given chance to present my paper. My name is Gizo Debito. I'm from Mizan-Tepi University College of Natural and Computational Science, Department of Mathematics. My presentation paper title numerical solution of one-dimensional Schrodinger equation using radial-based quadrature method and the cubic spline function. Here are some of the presentation outline, introduction, statement of the problem, study procedure, result discussion, definition, and the last one is conclusion. And now the first one, introduction. The partial differential equations are the mathematical equations that are significant in modeling physical phenomena that occur in nature. Applications of these partial differential equations are found in physics and engineering and mathematics. Also, the applications of these partial differential equations are found in different area of science. Majority of partial differential equations do not have analytic solution. So it is important to obtain accurate solution numerically. So many computational methods have been developed and implemented to successfully to approximate the solution of this partial differential equation. Among these, traditionally mesh-based methods like finite element, finite difference, and boundary element methods have been used according to this author. So these methods require the mesh or the grids as a solution domain. The major problem of these methods are the cost and the difficulty in in creating the mesh. So to avoid the mesh generation, mesh-based methods like radial-based function quadrature methods are important to solve or to give the approximate solution of such kind of partial differential equation. Okay, so therefore, mesh-free methods are the meshless in a way that they do not require the connectivity of grid or mesh points. However, finding the nearest neighbor is computationally less intensive than mesh generation in mesh-based method according to NACFI 2013. Therefore, radial-based function methods are mesh-free methods which compose a univariate basic function with Euclidean norm, which turns multidimensional problem into one-dimensional and makes the problem insensitive to dimension of the problem according to this author. So among these different radial-based functions, the multi-quadric radial-based functions we center at xg, yj, and cj written in the form of the equation here in one dimension, two-dimensional, and three-dimensional problems respectively. As a result, methods that use a radial function for their base functions are easily adopted to solve the problem in high-dimension problems. So due to the meshless and the ease of implementation property of radial-based function, the use of C1 cubic spline collocation method to obtain the approximate solution in the form of spline over the entire area of the region of the problem. So this study used multi-quadric radial-based differential quadrature method to approximate the spatial derivative and the C cubic spline collocation method to solve one-dimensional Schrodinger equation in the form of this as shown in equation 1.1 with initial condition given here and the boundary condition is given in 1.3. So in this equation 1.1, u of xt is a wave function, omega of x is arbitrary potential function is I is square root of -1. Therefore, Schrodinger equation is also called Schrodinger wave equation, which is a partial differential equation that describe how the wave function of physical system evolves over time. So according to the Dagan and Shorky 2007, the application of Schrodinger equation found in various quantum dynamic calculation. For this, the purpose, the construction of efficient numerical method for solving such Schrodinger equation is an important task. Many different authors also proposed put the method for the solution of the Schrodinger equation. Among these, Sabarian and Radpur 2014 proposed compact finite difference scheme and the C1 cubic spline collocation method used for solving one-dimensional Schrodinger equation. So the method gives both point-wise approximation at all the mesh point and the cubic spline collocation or solution in each space step. However, the accuracy and the efficiency of the method needs further investigation. To this end, this study presents accurate, convergent, and efficient method for solving one-dimensional Schrodinger equation based on the radial-based quadrature method for approximating spatial derivative and the C1 cubic spline collocation method for time derivative. Here is the objective of the study. The general objective of this study is to develop radial-based quadrature method and the cubic spline collocation method for solving one-dimensional Schrodinger equation. And the next one are the specific objectives to describe the solution domain, to replace the spatial derivative in one-dimensional Schrodinger equation, to apply the C1 cubic spline collocation method on the linear system of ODE, to investigate the stability and convergence of the method, to compare the approximate result with the exact solution, and finally to describe the advantage of the present method over other numerical method. Here is the steady procedure. In order to achieve the intended objective, the following mathematical procedures are listed. The first one is describing the problem. The second one, discretizing the solution domain. The third one, replacing the derivative involving a spatial variable by the sum of the weight coefficient times functional value as a grid point. The fourth one, solving the resulting linear system of ODE by C1 cubic spline collocation method. The other one, establishing the stability of the method. And the last one is validating the method using numerical example. Here is the resultant discussion. So let us consider one-dimensional Schrodinger equation time dependent in this form with initial condition and boundary conditions. So in these equations, f, g1 and g2 are the known functions and assume they are continuous function. To approximate the derivative in this partial differential equation or in this one-dimensional Schrodinger equation, first the two intervals are divided into n and m equal subintervals of the mesh lengths h and k respectively. Therefore, let a is equal to x1 less than xn1, x0 less than x1 less than xn is equal to b for the space direction, and 0 is equal to t0 less than t1 less than up to tm, which is equal to tb. The mesh points with the xl and the tj given for l and j, that is l1 up to n and j1 up to m. The next one is replacing this spatial derivative by using radial-based differential quadrature method. So in this radial-based differential quadrature method, the derivative involving spatial variable is approximated by the sum of weighting coefficient times functional value as the grid points. So to approximate the derivative of u of xt for the L's node, we can write this second derivative as this equation 4.1. So from this, ALJ is the weighting coefficient to be determined, and T is the temporal or the time direction. So the other one is determining the weighting coefficient. So in this section, the weighting coefficients in equation 4.1 are determined. To find this, the weighting coefficients radial-based function, particularly multi-quadric radial-based function, is applied among the other different or commonly used radial-based functions. So in one-dimensional space, the multi-quadric radial-based function is given by this equation 4.2, where c is the positive constant, which is known as shape parameter. Then the first and the second derivative of the multi-quadric radial-based function is equation 4.2 are given in the following 4.3 and 4.4. Now, since this pi j of xt is a base for one-dimensional space, by the properties of vector space, we can write this u of xt by the equation or like equation 4.5 for at least one lambda j different from 0. So after some manipulation or simplification, now the weighting coefficient LG at each L node can be achieved as equation 4.10. So this equation can also be written in other linear equation in the form of equation 4.11 and matrix, or in matrix equation form AC is equal to B, where A, B, and C are written below here. So therefore, the solution of AC, which is equal to B, gives the weighting coefficient of this LG. But according to this Kosari and Sfarian 2017, parametric radial-based function like multi-quadric radial-based function, inverse multi-quadric radial-based function, and Gaussian have very interesting properties. They are smooth and infinitely differentiable. And interpolating or solving partial differential with this parametric radial-based function, the resulting system matrix is non-singular, and thus interpolating or solving PD with these functions has a. Therefore, the system matrix A in the equation 4.12, which is obtained by using multi-quadric radial-based function, is non-singular and invertible. As a result, the system in equation 4.12 is solvable and has a unique solution. Hence, the weighting coefficient LG as obtained in equation 4.13. After the determination of the weighting coefficients, the equation 1.1 can be written as in this form. And at L's node, this equation 4.14 can be also written in this form. So since the XL are known, equation 4.15 become the ordinary differential equation. That is, once we are able to generate the weighting coefficient LG, we obtain a system of ODE in n minus unknowns, which can be solved by any standard method. So the other one is solving linear system of ODEs, that is the resulting equation. In this section, we apply the C1 cubic spline collocation method to solve a system of ODE and equation 4.16. In order to get a unique solution for the problem, let us assume m is equals to n. So equation 4.16 can be written as equation 4.17. And in this equation 4.17, D and E represents the two different matrices. And also this U, the first derivative of U with respect to T, and also U of T represented like this. And F is a vector value function, which is a function of T and U. So equation 4.17 can be written as this equation 4.18. And now let the U of T, capital U of T, be a vector that approximates U of T such that each of its component is a cubic spline function, or that is component-wise vector value function. Now suppose that this capital U of T satisfies the equation 4.18 at the correlation points like Tj minus 1, Tj minus half, and Tj, and the interval Tj minus 1 and Tj for j greater than or equals to 1. That is, it can be written in short equation form like this. So according to these authors, the unique cubic spline capital U of T defined in this interval is given as this, where the L of S and Q of S and V of S is written in this form, and S is an element of the closed interval containing 0 and 1. So to approximate the spline solution U of T, capital U of T, to exact solution of U of T, equation 4.18 are constructed as according to these authors. That is Uj given in this equation 4.20 and Uj minus half given in equation 4.1. With Uj means U at Tj, U prime at J means is the derivative of U with respect to or with to UTJ and so on. So equation 4.18, in equation 4.18 or using equation 4.18, we can write equation 4.20 and 21 respectively as this form. So after some manipulation or simplification, the resulted equation is given us in this form where I is the identity matrix. And also we rewrite the equation 4.29 in the following form for j greater than or equals to 1. Now, the relation given in equation 4.3 is a linear system of n minus equation. By solving this equation for uj, for j1 up to m, and then using equation 4.1819 and 4.21, a cubic spline approximation of uxlt in tj and tj minus 1 and tj can be obtained. The other one is stability analysis. To investigate the stability of the proposed method of equation 4.29, let us define G is equals to IB plus IE, and then equation 4.29 can also be written as in this form. So again, from this equation, we have Uj is equals to H times Uj minus 1 for J1 up to M. And here, H can be written as in this form, which is a matrix valued a rational function or the amplification matrix. And now let lambda be an element of the complex number, be an eigenvalue of G, and let Z is equals to K times lambda, means K is the step size for time direction. Now, here is one definition. A numerical method is said to be astable if its region of absolute stability includes the entire complex half plane with negative real parts. So, for the stability of the method, it's necessary that the absolute values of the eigenvalue of amplification matrix H, which is less than 1, that is, can be written in this form. And since Z is equals to K times lambda, we can solve for K is Z over lambda by using this relationship, and also let Z is equal to A plus BI. So, and Z1 as represents the numerator in this absolute value and Z2 the denominator. Now, by the modulus of complex numbers Z1 and Z2, we can have equation 4.35 and 3.6. So, by absolute value property, the equation 4.34 can be written as in this form. Based on the value of this absolute value of Z1 and Z2, equation 4.35 and 4.36 can have, or we can conclude from this value that this is less than this if the value of A less than 0. That means depending upon the value of the absolute value of Z1 and Z2, and Z1 is greater, absolute value of Z1 greater than Z2 if A is greater than or equal to 0. Now, therefore, in the relation 4.34, it is true if the real part is less than 0 and ZB in the left half plane, hence the proposed method is astable according to the definition given above. Now here is the other definition, that is the part approximate to E raised to theta. Assume that E raised to theta is approximated by this equation, where Cs plus t plus 1 is a constant. The rational function Rst of theta is given in this form, which is Pt of theta over Qs of theta, is called St par approximant of order S plus t to E raised to theta and has leading either term of order S plus t plus 1 according to these authors. So based on the definition of 4.5.3, the rational function R22 of theta can be written in this form and is known as a 2-2 par approximant of order 4, that is 2 plus 2 to theta E raised to theta, which has a leading either term 2 plus 1, which is 5, according to this author. So equation 4.33, in equation 4.33 is the amplification matrix, or the matrix value of rational function H is a rational function which can be written as R22 of Kg, and which gives this equation, which is called a 2-2 par approximation of order 2 plus 2 to E raised to kj and has a leading either term also 5. Therefore, the method has fourth order accuracy in time. So the other one is the error boundary rate of convergence. Here is the other definition. A numerical method for solving this equation is convergent if the maximum of pointwise error or absolute error is tends to 0 as k approach to 0. For 0 less equal to j less or equals to t over k is a step size for time. Therefore, the other definition is 4.6.2, rate of convergence. Assume that the function f of tu is sufficiently smooth. In particular, we need f of t to have a p continuous derivative that is up to and including this. So a numerical method to solve this equation has order of p if the maximum pointwise absolute value of the error is less or equals to the order of p as k approaches to 0 or for sufficiently small k. So since our proposed method is fourth order accuracy theoretically in time, therefore we can write this above equation in the form of this, that is the largest or maximum absolute value error of pointwise approximation is less or equal to this. Hence, the proposed method converges for this relation for sufficiently small k. Here is a numerical example. One problem is solved by applying the present method to enable us to compare our result with the earlier work. The problem is taken from the existing literature, that is Herian and Radford 2014. Here, consider the example like one-dimensional Schrodinger equation like this, and from this 1 minus 2 over x squared is represented as omega of x, that is arbitrary potential function, with whose exact solution is this, with the initial and boundary conditions like this. So the maximum absolute error of pointwise approximation and the order of convergence of the real part and the imaginary part of the solution of the problem for different values of the step size in space and temporal at time t is equals to 1 are presented below the next page, and the maximum error and the experimental convergence order of the method that is denoted by C order at t is equal to 1 are defined as in these two equations. That is, this is the largest or the maximum absolute value pointwise errors, and this is the experimental order, that is convergence order, which can be calculated by using this relation for, that means for step size h and k and h over 2 and k over 2. So using this relation in table below, okay, so table 4.1 shows the absolute maximum error and the experimental convergence order for the problem present and the Siberian and Radbourg. So PM means by present method and SR means by these two authors. Therefore, different mesh sizes, mesh size 1 over 5 for example, in present method for the step mesh sizes 1 over 5 for real part. Here it gives this result, and for this it gives this result. And also for the imaginary part here, can compare from this. And by using the relationship of C order in present method, the experimental convergence order gives this, and the previous or earlier method gives this. So similarly, the imaginary part, it gives this, and the difference is that here approximately the experimental convergence order is 4. Here in the earlier method it is 2. That is therefore the present method in the discussion part, in this section, the numerical results and order of convergence are presented. As it can easily be seen from the table, the numerical order of convergence is a good agreement with the theoretical order of convergence, as well as the present method gives better approximation with no further mesh refinement is required. Finally, the present method is more accurate and efficient than the method presented by this earlier work. So the last one is conclusion. In this thesis, numerical method for solving one-dimensional time-dependent Schrodinger is presented. We applied multi-quadric radial-based function to approximate the derivative involving spatial variable and C1 cubic spline corrugation method for time component to solve one-dimensional Schrodinger equation. The stability, error bound, and the theoretical order of convergence are well established, and hence the method is astable, and the numerical order of convergence is a good harmony with theoretical order of convergence. And the method has further accuracy in both time and space and experimentally obtained result, and it is suitable for long time interval. Finally, the numerical result presented in table confirms that the capability of the method for solving one-dimensional Schrodinger equation. Thank you. This is my presentation.
Okay, Mr. Gzau, thanks for your nice presentation.
Okay, thanks.
Now I have one question.
Okay.
What is the real-life application of one-dimensional Schrodinger equation?
Okay, Schrodinger equation is a fundamental equation in physics that describe how the wave function changes in time. So to solve such kind of a problem in physics, it is very important.
Okay.
Any other question?
I do have some questions.
Okay.
Mr. Guido,
Yes.
thank you for your nice presentation. I do have some questions. For
Okay.
instance, in the radial basis quadrature method, as you mentioned in your introduction part, there is no meshing, you said. And in reality, there is no meshing. As a result, we cannot use that of the Taylor series expansion. And we cannot do analysis, the like of order of convergency, and that is consistency, and that of convergency. Is that not?
Yes.
In your conclusion part, you said that the method has both fourth order of convergency in the space direction and in time direction. In reality, the order of convergency you have shown is for that of the C cubic spline, I think. Is that not?
Of course.
So how do you know that whether the order of the method is 4 in the direction of time, in space?
Okay, I said an experimentally obtained result, not in theoretical part, an experimentally result from the table. The convergence order is calculated by using the relationship given for the step size in H and H for space and K for time. Due to this reason, I said fourth order in both two, but theoretically, I obtained only for time.
Theoretically, you have obtained fourth order convergence for the temporal direction.
Of course.
Okay, the other question is the problem in the radial in the quadrature method is that how to find the shape parameter. It is difficult to obtain. It's possible, but it is in some circumstances it is difficult to get the optimal shape parameter. Have you used the optimal shape parameter, or you have randomly selected some shape parameters for your particular problem?
Okay, the optimum shape parameter may be different depend upon the governing equation and the type of the problem, and also it needs further investigation. I used randomly or the anterior and error method.
Okay, thank you. One recommendation is it is better to add at least one numerical example to make it more sound. Okay.
Okay, for the future.
Thank you for your nice presentation. Have a nice time.
Okay, thank you for your nice question.
Any other question? Any other participant who did present his work and he want to present?
Yeah,
Mr. Alonso,
yes.
kindly share your screen.
Okay. Yes, Doc. Is it available?
In the process.
Yeah, it's available.
Okay.
It's visible.
Is it visible?
Yes.
Okay, thank you very much for your interesting international conference. First of all, I would like to set the outlines of the thesis. This is an abstract and we'll have an introduction. And after this one, we'll have a model analysis. After this model analysis, we'll have a numerical results and analysis, and also we'll have a conclusion, and there will be references for such each and every thing here. The first one is in abstract. In this study, an autonomous type deterministic nonlinear mathematical model that explains the transmission dynamics of COVID-19 is proposed and analyzed by considering the awareness campaign between humans and infected of COVID-19 asymptomatic human immigrants. Unlike some of other previous model studies about this disease or COVID-19, we have taken into account the impact of awareness campaign between humans and infected of COVID-19 asymptomatic human immigrants in the transmission of COVID-19. The existence and uniqueness of the model solutions are proved using fundamental existence and uniqueness theorem. We also showed that positivity and the invariant region of the model system with initial conditions in a certain meaningful set. The model accepts two equilibrium points which are disease-free and persistent of COVID-19 equilibrium points, and also the basic relation number is derived by using the next generation approach. According to our analytical analysis of the model, this equilibrium point is obtained only in the absence of asymptomatic COVID-19 human immigrants and COVID-19 in the population. Local stability of the disease equilibrium point is verified via the help of Jacobian and Hurtuz criteria, and the global stability is verified by using Castillo-Chavez and Song's approach. The disease-free equilibrium point is both locally and globally asymptotically stable whenever R0 is less than 1, which implies the disease dies out in the population. If R0 is greater than 1, the disease-free equilibrium point is unstable, while the endemic equilibrium point exists and stable, which implies the disease persists and reinvention will occur within a population. Finally, some numerical results are illustrated to verify the theoretical results of the model. Introduction. Here, coronavirus are a large family of viruses that may cause illness in animals and humans, and it is caused by novel coronavirus severe acute respiratory syndrome 2. In December 2019, the first COVID-19 was identified in Wuhan, China, with common manifestation appear to be pneumonia. COVID-19 is transmitted from human to human via direct contact with contaminated surface and through respiratory droplets, inhalation from infected individuals with common symptoms including fever, dry cough, shortness of breath, and fatigue. The World Health Organization, WHO, declared the outbreak of this COVID-19 as a public health emergency of international concern on January 2020 and as a pandemic on 11 March 2020. Since COVID-19 outbreak, different scholars studied the transmission dynamics of the disease by considering different scenarios on how to combat or control the spread by using epidemiological mathematical model. Unfortunately, aforementioned mathematical model studies failed to consider the level of awareness between humans and the immigration of COVID-19 asymptomatic individuals in the transmission of COVID-19. So that in this study we are inspired or motivated to consider the impact of awareness among individuals and COVID-19 as migrants in the transmission of COVID-19. In order to proceed this study, susceptible human class are classified into aware susceptible and unaware susceptible class. Therefore, in our model, the total number of human population at a given time t is denoted by NH of t, and it is categorized into 6 subclasses as a susceptible human population class, aware human population class, unaware human population class, and exposed and infectious, and finally, this is a recovered human population class. With regard to the above considerations, the compartmental developed COVID-19 model flow diagram is shown in this here. This is SH is a susceptible human class, and SUH is an aware susceptible human class, and AH is aware susceptible class, and AH is an exposed human class, IH is infected, and RH is recovered. And such this each and every parameters are described from their description. The above scenarios and the flow diagram one leads to the following autonomous system of nonlinear differential equations. This is given by this one, 6-dimensional system with initial conditions here, and this theta and tau are progression rates or proportion rates, not progression rates, they are proportion rates. Let's come to our model analysis. The first one is existence and uniqueness of solution. Since the autonomy and the validity of any mathematical model depends on the existence and uniqueness of solution, so first we have to show that the existence and uniqueness of solution. This is achieved or established by this theorem. If the initial data be this one to the system of equations which is given from the above, then there exists a unique solution in R6 for all t is greater or equal to this one. This is verified by the right-hand side of each for system equation one is continuously differentiable almost everywhere in R6, which implies f is locally Lipschitz. Hence, by the fundamental existence and uniqueness theorem, there exists a unique solution locally in R positive R6 for model system 1 for all time t greater or equal to 0. Since the system of equations monitors the human population, so each and every solution must be non-negative or it must be positive. So this is achieved by this one. If the initial conditions are this one, then the solutions are non-negative for all time t is greater or equal to 0. It is non-negative in place, almost is positive. From the model equation 1, consider the first equation. When we consider the first equation using integrating factor method, the solution becomes this one. Hence, as t goes to infinity, this, or as t goes to large, this term goes to 0, and only this term is remain. So this term is greater or equal to 0. So the class of susceptible human populations are positive. From model's equation 1, consider the third equation. This is given by this one. Assume that for the first time t1, the unaware human population at time t1 is 0 and its derivative is less than or equal to 0. And it is true that others are positive for 0 less than t is t1. T where t is between 0 and t1. Based on our assumption, we'll have this one because this term is 0. This term and this term are 0, so this term is a remain. Then we can find the solution for this one by using this is a separation or whatever it is. The solution for SH is obtained from the above, so this is greater or equal to 0 because as t goes to 0, as t goes to large, this term goes to 0 and only this term is a remain. So this is positive. It can be shown analogously that for other class of human populations are positive for all time greater than or equal to 0. Hence, the positivity of the solutions are achieved. The invariant region. There exists a domain omega, a domain sigma in which the solution set, this one of model 1 is positively invariant. The time derivative along the total human population S size NH and after some mathematical manipulations will have this one. From this one, in the absence of COVID-19 asymptomatic human migrants and using integrating factor method, we'll have this one. So as time t goes to infinity or large, it terms goes to 0, and hence this nh of t is less than or equal to lambda h over ah. So this is positively invariant. this is positively invariant. Let's come to this FICRRM point of the model. We calculate the disease FICRRM point of the model system 1 represented by E0 by equating all the right-hand side equations to zeros and putting the infective class equal to 0. Then we obtained this one. This can be interpreted in epidemiological point of view. E0 can be represented as in the absence of infectives in the community and COVID-19 asymptomatic human migrants, only susceptible human, our susceptible human, and our susceptible human population exists in the community or in the population. Let's come to basic reduction number threshold parameter here. Using a next generation approach method, we'll have this one, and after this one, we'll have the Jacobian matrix Fi, and if we at the disease FICRRM point of E0 is given by this one, F and V respectively. This is given by this one. From this one, when we calculate or when we find the inverse of V1, we'll get this one. Finally, when you get F times V inverse is equal to this one. From this one, we will have one eigenvalue here and another eigenvalue 0. The two eigenvalues of F times V inverse are here. So this is the maximum, or this is the spectral radius of the Jacobian matrix, this one. So this is the basic correlation number for our model. From the basic correlation number R0, which is given by from the above, this one, 1 over alpha H plus delta H minus eta H refers to the average duration of human population in exposed state to become infectious or recover, and 1 over alpha H plus rho H plus gamma H is the average duration of the infectious period of human populations until they die or recover from their disease. The stability behavior of the disease FICRRM point of the model. The disease FICRRM point of the model is this one, is locally asymptotically stable if R0 is less than 1 and unstable for if R0 is greater than 1. The Jacobian matrix of the system, at the disease FICRRM point E0 is given by this one. From this one, this is the block matrix. One can see that this is the block matrix, and we'll have this one, another block matrix. Then we'll have, or you can simply calculate the characteristic polynomial of this is given by this one. From this one, you can calculate the eigenvalues. The 4 eigenvalues of the Jacobian matrix at the disease FICRRM point is lambda 1 this one, lambda 2 this one, lambda 3 this one, and lambda 4 this one. And the remaining eigenvalues are obtained from this characteristic equation. From this one, we can recall the resources criteria. Let's see, A0 is equal to 1. If which is greater than 0, A1 is positive and A2 is here. When we simplify or manipulate, or further manipulation of this one is R0. So from this one, you can deduce that whenever R0 is less than 1, this one is stable or it is positive, hence the required result. Existence and local stability of the endemic steady state. Let this is the endemic steady state. This implies all components are positive. And components of are obtained by making the right-hand sides of model expressions to be 0, and after some mathematical manipulations, we get this one. These are the endemic problem points. Let's see the sensitivity analysis of the basic correlation number. The normalized forward sensitivity index of R0 that depends differentiable on a parameter P which represents model parameters is defined by this one. The sensitivity analysis indices evaluated as the baseline model parameters values are resembled from table 1, which is given from below. The sensitivity indices are arranged in descending order as follows. This is numerical results of sensitivity indices. This is the results of this. From this one, the positive indices shows that this have a negative impact in the control of COVID-19, and this negative index shows that this has a positive impact in the control of COVID-19. So one can decrease these positives and one can increase this one in order to control the COVID-19 pandemic. Let's see the numerical simulations of the model graphics for general dynamics. To illustrate the analytical results of our model, numerical simulations are carried out using MATLAB OD45 solver with the following initial conditions here. From this one, one can see that all the infective class goes to 0 and non-infective class goes to non-zero components, and R0 is greater than 1. Less than 1, so that this is R0 is less than 1, so that all disease or infective class are goes to 0 or tends to 0, and non-infective class tends to non-zero. And from this one, one can see that all components are above 0 or tends to non-zero components because R naught is greater than 1. This implies both the infective and non-infective populations coexist. This is the epidemiological implication. This result is that disease or COVID-19 will die out in the community regarding to continuous awareness created between humans and create impasses in or great impasses in the control of COVID-19 asymptomatic human immigrants. This is the explanation for the above figure. This is from here. When we increase the recovery rate of infectious humans, and when we increase the immunity of the recovered human populations, then the aware human populations increase. And from this one, when the values of the rate of infected immigrants increase, then the number of exposed human populations increase. This is the relationship between individual parameters with basic rational number. They have the direct proportional with R naught. And from this one, this is when we keep the values of the contact rate of human populations with humans either exposed or infections with susceptibles constant with between 0 and 1. And when we decrease or increase the values of the infected immigrants, it will increase the basic reproduction number. This increase the basic reproduction number implies that the disease will spread within the population. This is similar to this one, but when this one is when the values of the infected immigrants mix or becomes large, then the basic reproduction number becomes large. So this is the explanation for this numerical results. This is the conclusion and recommendation of our research. And this study, a nonlinear deterministic mathematical model of COVID-19 pandemic is developed and analyzed to investigate the impact of awareness campaign and COVID-19 asymptomatic human migrants in the transmission of COVID-19. We first obtained the domain where the model gives epidemiologically meaningful and mathematically well posed by the fundamental existence and uniqueness theorem. Both positivity and boundedness of our model solutions are shown analytically. The basic rational number R naught is computed using next generation matrix approach. The analytical analysis shows that the disease-free equilibrium point and endemic equilibrium point of the model exists under certain conditions. We analyzed both the local and global stability of the disease-free point of the model based on R naught. The disease-free point of the model is locally as well as globally asymptotically stable whenever R naught is less than 1 and unstable whenever R naught is greater than 1. From epidemiological point of view, the disease or the COVID-19 will die out in the population whenever R naught is less than 1 and persists in the population whenever R naught is greater than 1. Positive indicator point of the model exists and it is locally asymptotically stable whenever R naught is greater than 1, so that the reinvention of COVID-19 may occur within the population. We performed sensitivity analysis of the basic reproduction number with respect to model parameters to identify which parameters have a strong influence on the dynamics of the system or the COVID-19. Both analytical analysis and numerical simulations results of the model assured that the most sensitive parameters for the transmission of COVID-19 are beta and the proportion rate theta, while the most sensitive parameter in the control of COVID-19 transmission is the propagation rate delta followed by gamma h. These are references. Thank you very much for your invitation for this marvelous conference. If you have any question, welcome. I have finished my decision.
If you have any question from the audience part, you can raise your question. Thank you for your nice presentation, Mr. Alamzad. From the audience, if you have any question which needs some clarification from the presenter, it is your time. Okay, Mr. Mitaku, you can raise your question.
Okay, welcome. Yes.
Please continue your question from the audience parents.
I have one question.
Okay.
You can
Welcome.
continue.
Okay, Mr. Alamzot,
Yes.
thanks for your nice presentation.
Okay.
I want to ask you some questions.
Okay.
You say that when R not less than 1, the disease will be dies out.
Okay.
Is that possible? Is that you conclude that always when R not less than 1 is the disease will be dies out?
Yeah, based on our model, and based on the preconditions, the disease will be dies out because we are assuming that there are a class of populations who have awareness class of populations. So if there is an awareness and if there is no infected immigrants, and after a long period of time, this will be dies out in the population when R naught is less than 1. This is based on our preconditions.
Okay, but I think it is more reasonable when you do bifurcation analysis. If your model is undergoes under forward bifurcation, is that this is possible when R not less than 1, the disease will be dies out. But if the model undergoes an backward bifurcation, in the case of backward bifurcation, when R not less than 1, there is endemic run point.
Okay.
So that in the case of this, if R not less than 1, if there is endemic run point, the disease still persists in the population, but R not is less than 1. Therefore, in the case of backward bifurcation, we cannot conclude that when R not less than 1, the disease will be dies out.
Okay.
Or for more reasonable, I think if you do the bifurcation analysis, it is better.
Okay, it means I will conduct that one because mostly we use the bifurcation analysis when it is difficult to conclude about the local stability of the endemic point. Okay, yeah. If the analysis or the local stability analysis of the endemic point is difficult, we can apply the bifurcation analysis, but I cannot or I do not apply here. I will apply here. Okay, I will apply or I will look how it will be changed.
Okay, it is good. And now there is the next question.
Okay.
Why you consider only asymptotic infected immigrants? I think there is also infective immigrants. Therefore, in the infected compartment, you are not consider the infected immigrants.
What type of infected immigrants? For example, we'll have asymptomatic and symptomatic infected immigrants.
Yeah,
So,
I think in your model, you considers only asymptotic immigrants.
Asymptomatic, yeah.
Yeah, but there is also symptomatic immigrants.
Symptomatic immigrants, yeah.
Yeah. So why not consider symptomatic infected immigrants?
Here I did not put the assumptions of the model, but I have put the assumptions in the model. Okay, I did not consider the symptomatics of the human immigrants because mostly as a reality when we see that those populations who are showing the symptoms do not move anywhere. Okay, as a reality, it is not reasonable to put this one because if someone shows the symptoms of COVID-19, he may not move anywhere. Okay, anywhere. And also, I have put in assumption part. Okay.
Okay, it is good. Thank you for your nice presentation.
Thank you, Mr. Tanna, for your question.
I have the question, sir.
And thank you, Mr. Alamzod, for your clarification. I think, is there any question from the other audience?
Of course, I have.
Mr. Hailu Mulad, I think you have write some question, yeah?
Okay.
Is there anyone who have a question for Mr. Alamzod from the audience?
I really ask.
You can continue.
Okay, welcome.
Who would like to ask the question to Mr. Alamzod?
I said welcome.
Okay. If there is anyone who would like to ask any question, thank you for your presentation and the clarification, Mr. Alamzod. I would like to
Thank you very much.
Thank you so much, Mr. Alonso.
Okay.
Is there any suggestion from participant side? Actually, we are going to close this conference. If you have any suggestion you want to give us, please raise your hand.
Okay.
I will give you a chance to share your opinion or suggestion with us.
Okay. First of all, I would like to say thank you very much for your various international conferences. And I am always proud with my previous or former department colleagues for this prosperous international conferences. And I would like to say thank you a lot. And you have to continue by such a way. You are a role model of in any department from the college. So you are the role model for other departments, and I hope all other departments will follow your role model or your actions or activities in participation. Thank you very much again.
Any other who want to share his views or suggestions with us? Okay, yeah, sure.
Dear participants of conference, my name is Mr. Okudama, a Department of Mathematics from under College of Mechanical Computational Science from Mizan-Tepi University. I would like to express my heartfelt thanks to each. I would like to express my heartfelt thanks to each of you who participated in the first international conference on recent researches in mathematics that we completed today. In this conference, many participants have participated in different areas of the world and presented many nice and wonderful papers about recent research mathematics. This is the reason, as a department, as a college, and as a university, we can say very happy and successful. As a department, I would like to give special thanks to the speakers of the conference for hosting us during the event, for all committee members who worked on the success of this conference. Finally, I hope we will join in the future by another conference with the side of you and us. Thank you very much.
Now I request Mr. Buzuwar to present a certificate of appreciation to today's keynote speaker, Dr. Mamta Thakur.
Thank you very much. Actually, I would like to say thank you all participants present here for their devoted and committed to attend our international conference. And I would like to say thank you very much, Dr. Mamta Thakur, sorry for my pronunciation of the right spelling of her name. She spent her time with us to give us a good explanation. And I would like to say thank you.
Thank you so much, sir. Now I request Professor Dr. Meher Chand to present Certificate of Best Paper Presentations. Professor Dr. Meher Chand.
Thank you, sir, for inviting me. First of all, many congratulations to the entire team to organize first international virtual conference on recent researches in mathematics 2022. And thanks for giving me the responsibility for the announcement of Best Paper Award. The papers which are presented in this conference really very quality work is there, and recent advancement based papers are presented in this conference. But one of them is best paper title chaotic dynamic in cannibalistic predictor system with harvesting, presented by Harsha Karbanda and Mr. Mohammad Fias. Paper ID is FICRRM-22 /13. So this is the best paper which is decided by the organizing committee. And now I would like to ask please to share the best paper award to the participant, and many congratulations to Harsha Karbanda and Mr. Mohammad Fias for this best paper award.
Thank you so much, sir. Now I would like to request Mr. Buzuwar to give vote of thanks. Mr. Buzuwar.
Thank you, sir. Thank you. By Muhammad Fayaz.
Thank you very much. Good afternoon, ladies and gentlemen. On behalf of Mizan-Tepi University Academic Unit, in particular the Department of Mathematics under College of Natural and Computational Science, the entire others supporting and organizing team and crew, let's give me immense pleasure to deliver vote of thanks to this conference. First of all, I would like to thank His Excellency, Honorable President of Mizan-Tepi University, Dr. Ahmed Mustafa, under his added supervision and moral support, we are able to organize this conference. I would like to thank Dr. Temesgen as well, Vice President of Business and Development, Dr. Temesgen, always monitoring and give suggestion towards organizing this conference. And the third, I would like to pass my thanks to Dr. Abid Asad, Vice President of Research and Community Service of Mizan-Tepi University. Dr. Abid has accepted our proposal and motivated us to undergo with the organizing this conference, and he spent his valuable time with us to support us in the accomplishment of scholar conference indeed. And I would like to thank as well Mr. Kesam Mulad, the Vice President of Academic Affairs of Mizan-Tepi University. He also gave us his suggestion toward this organizing this conference successfully. I would like to also add my thanks Mr. Elijah Mamo, Chief Executive Officer of Tepi Campus. He is in spite of his busy administrative schedule involving many of preliminary meeting, and suggests us in proceeding the organizing of this conference in success. In addition to that, I would like to thank all the keynote speakers for accepting our invitation with terms and participating today in this the last two-day conference. And moreover, I am very much grateful to pass. My intent is to conference committee, organic committee, especially for Mr. Sakai Rasha, TEP Campus Research and Community Service, Technology Transfer, and also Mr. Linkage Director, Mr. Onumani Adis, TEP Campus Academic Program Director, Mr. Ogayo Gala, International Relationship and Partnership Directors, Mr. Atai Shatu, Business and Development and Administrative Directors of TEP Campus, Mr. Jonas Gietong, Delegated ICT Director of TEP Campus, as well Mr. Workutelna, Head Department of Mathematics, and also the whole staff of the Mathematics Department give to us their valuable time for their busy administrative schedule and the many of preliminary meeting and suggest as in proceeding the organizing this conference successfully. My special thanks is to go through the Dr. Muhammad David Idris, Associate Professor in Mathematics, Department of Mathematics, and College of Natural and Computational Science of Mizan-Tepi University, and also Dr. Shamuga Sunram, Associate Professor in Mathematics at the Department of Mathematics in the College of Natural and Computational Science, to organizing, chairing, hosting of this 2 days conference. Last but not the least, I would like to thank all the participants, organizing committee member, editorial board member, dean of all college, all head of the department, faculty of Mizan-Tepi University, particularly College of Natural and Computational Science under Mizan-Tepi University, for their participation in the last 2 days conference with patience and gave a suggestion and a comment to accomplish this conference with great success. I thank all of the participants.
Thank you so much, sir. Being a host of the conference, I am very thankful to all our keynote speakers, paper presenters, participants, and all the committees taken part in this conference. Thanks to all of you to make this conference success. I would like to give special thanks to Professor Dr. Meherchand, Professor Mamta Thakur, and Dr. M. Shehbazullah for their cooperation to conduct this conference. Without your cooperation, it was not possible to conduct this conference in such a nice way. Again, I thank to all of you. In future, if you need any academic assistance from our university, and especially from our mathematics department, please feel free to contact us. I wish a very happy, healthy, and bright future to all of you. Thank you so much. Now we are going to close the conference. Thank you.
Thank you.
Thank you very much.